In the vast cathedral of space, where darkness reigns supreme and silence stretches across distances that mock human comprehension, there exists an unwritten law. Things do not glow unless they burn. Stars shine because nuclear furnaces rage in their cores. Comets develop luminous tails when ancient ice meets solar heat. Even the faint gleam of planets reflects borrowed light from their parent stars, mirrors catching fire from distant suns. This cosmic darkness is not empty. It pulses with invisible radiations, hums with magnetic fields, and dances with particles streaming between worlds. Yet to our eyes, accustomed to the bright day and electric night of Earth, space appears as the deepest black imaginable, punctured only by the pinprick illumination of objects hot enough or large enough to betray their presence across the astronomical gulf. Most interstellar visitors honour this darkness. They drift through our solar system like silent shadows, reflecting barely 4% of the sunlight that touches their surfaces. When Oumuamua tumbled past in 2017, humanity's most powerful telescope strained to glimpse its dark form against the star field. It appeared as little more than a moving point of light so faint that automated systems initially dismissed it as instrumental noise. Borisov, the interstellar comet that followed 2 years later, remained invisible until solar heating began to vaporize its ancient ices, creating the gossamer tail that announced its alien origins. These visitors followed the rules. They came from the darkness, passed through our brief window of detection, and returned to the darkness, their surfaces cold and unreflective as charcoal, their presence known only through the patient vigilance of astronomers who scan the sky each night for anything that moves against the background of supposedly fixed stars. But in October of 2024, something changed. Something broke the ancient covenant between interstellar space and cosmic darkness. 3IATLAS had been discovered 18 months earlier, another dark wanderer following a hyperbolic trajectory that would carry it past the sun and back into the void. Initial observations catalogued it as unremarkable. Roughly 800 meters long, tumbling end over end every 7 hours, its surface dark as volcanic rock. Spectroscopic analysis suggested a composition similar to carbonaceous asteroids, rich in organic compounds, but lacking the volatile ices that might create a visible coma when heated by solar radiation. For months, it behaved exactly as expected. Telescopes tracked its approach with the mathematical precision that makes astronomy possible, plotting its course through the solar system with calculations so accurate that observers could predict its position weeks in advance. It was a textbook interstellar visitor, obeying every law of celestial mechanics and optical physics. Then, 3 weeks after its impossible course correction, the luminosity monitoring systems at the Atacama Observatory detected something that should not have been possible. 3IATLAS was glowing. The anomaly emerged gradually from the data, like a whisper growing slowly audible in a silent room. Automated brightness measurements began showing values that didn't match the predicted reflectance calculations. At first, astronomers assumed instrumental error or atmospheric interference. Such deviations are common when observing faint objects at the limits of detection, where a passing cloud or slight mechanical vibration can skew measurements beyond their margins of uncertainty. But the discrepancy persisted. Night after night, observation after observation, 3IATLAS appeared brighter than it should have been according to every known principle of how light behaves in space. The object was glowing at visual magnitude 8.2, when calculations based on its size, distance, and estimated surface composition predicted it should barely reach magnitude 11.7. In astronomical terms, this represented a brightness anomaly of nearly factor 12. The wandering mountain was shining 12 times brighter than physics said it should, as if some internal light source were adding to the meagre sunlight reflected from its dark surface. Independent confirmation came swiftly as word spread through the global astronomical community. The Keck Observatory in Hawaii turned its twin 10-meter mirrors toward the anomalous object, while the Hubble Space Telescope adjusted its delicate pointing systems to capture high-resolution spectra of the mysterious glow. Each observation confirmed what the Atacama systems had detected. 3IATLAS was violating one of the most fundamental principles of observational astronomy. The albedo problem, as it came to be known, represented a crisis in our understanding of how interstellar objects behave. Albedo measures the fraction of incident light that a surface reflects, and for rocky bodies in space, This value typically ranges from 4 to 12%. Even the brightest asteroid surfaces, composed of highly reflective minerals, rarely exceed 20% albedo. Yet 3IATLAS was behaving as if its surface reflected nearly 50% of incoming solar radiation, despite spectroscopic evidence that it was composed of dark, carbon-rich materials that should absorb light rather than reflecting it. More puzzling still was how the brightness varied across different wavelengths of light. In visible wavelengths, the object appeared dramatically brighter than expected. In infrared, where warm surfaces should glow with thermal radiation, it appeared cooler than calculations predicted. In ultraviolet, where most surfaces become dimmer due to absorption, 3IATLAS maintained its anomalous brightness with remarkable consistency. This multi-wavelength behavior defied every model of how light interacts with matter in space. Normal objects follow predictable patterns across the electromagnetic spectrum, their brightness in each wavelength determined by their temperature, composition, and distance from illuminating sources. 3IATLAS seemed to be generating its own rules, shining with an intensity and spectral distribution that matched no known natural phenomenon. The distance factor added another layer to the mystery. As any object moves farther from its illumination source, its brightness should decrease according to the inverse square law, one of the most reliable relationships in physics. Double the distance, quarter the brightness, triple the distance, reduce the brightness by a factor of 9. This law governs everything from streetlights to supernovas, and it had never been observed to fail under any circumstances. Yet as 3IATLAS continued its journey through the solar system, moving steadily farther from the Sun, its brightness remained stubbornly constant. The glow neither increased as it had approached perihelion nor decreased as it began its journey back toward interstellar space. It shone with the same anomalous intensity regardless of its position, as if the laws of physics that governed every other object in the universe simply did not apply to this wandering mountain from the stars. Radio telescopes joining the observation campaign detected no corresponding emissions in their frequencies. Gamma-ray detectors found no high-energy signatures that might explain the visible glow. X-ray observatories recorded nothing unusual from the object's direction. Whatever was causing 3IATLAS to shine was operating exclusively in the narrow band of visible light that human eyes had evolved to see, as if the phenomenon were specifically designed to be noticed by observers on Earth. The timing correlation was perhaps the most unsettling aspect of the entire mystery. The glow had appeared precisely 3 weeks after the object's impossible trajectory change, as if the two anomalies were connected by some underlying mechanism that operated according to its own inscrutable logic. First, the wandering mountain had demonstrated the ability to alter its course through space. Now it was announcing its presence with a light that defied every known principle of how matter behaves in the cosmic void. As autumn turned to winter and observations accumulated, the astronomical community found itself confronting a phenomenon that challenged fundamental assumptions about the nature of interstellar objects. This was not simply an unusual asteroid or an exotic comet. This was something that operated according to principles beyond current scientific understanding, something that glowed in the darkness of space for reasons that natural philosophy could not explain. The implications rippled through every model and theory that attempted to describe how objects move and shine in the universe. If 3IATLAS could glow without obvious heat sources, if it could maintain constant brightness despite changing distance from the Sun, if it could selectively radiate in visible wavelengths while remaining dark in others, then either the laws of physics were incomplete, or something far more extraordinary was occurring than anyone had dared to imagine. What do you think could cause a mountain-sized object to glow 12 times brighter than physics allows? Share your thoughts as we dive deeper into this luminous mystery that challenges everything we thought we knew about light and darkness in the cosmos. In the immense darkness between worlds where silence and cold reign eternal, our luminous visitor had chosen to shine. But shine with what kind of light? And perhaps more importantly, shine for whom? As we prepare to explore the natural explanations that science demanded be tested first, we must remember that in the cosmic order of things, light in darkness is never accidental, never meaningless, and never without purpose. The glow had appeared. Now came the far more difficult task of understanding why. When confronted with the impossible, science does not surrender to wonder. It demands methodical investigation, systematic testing, and the patient elimination of every conceivable natural explanation before entertaining possibilities that challenge the fundamental order of the universe. The mysterious glow emanating from our cosmic visitor presented exactly such a challenge, requiring astronomers to examine every known mechanism by which celestial objects produce light. The first and most obvious suspect was sublimation, the process by which solid ice transforms directly into vapor when exposed to solar radiation. This phenomenon creates the magnificent tails of comets, those gossamer streams of gas and dust that can stretch for millions of kilometers across space. As a comet approaches the Sun, increasing heat vaporizes volatile compounds frozen within its nucleus, creating a glowing coma of released materials that reflects and scatters sunlight with ethereal beauty. Could our visitor be undergoing similar processes? The mathematics seemed promising at first glance. To account for the observed brightness anomaly would require the sublimation of approximately 200 tons of ice per hour, a rate that, while enormous by terrestrial standards, falls within the range observed for some of the most active comets in our solar system. Hale-Bopp, during its spectacular 1997 apparition, ejected material at rates exceeding 100 tons per hour during peak activity. But comets announce their sublimation through unmistakable signatures that extend far beyond simple brightness increases. The vaporized materials create distinctive spectral emission lines, molecular fingerprints that allow astronomers to identify specific compounds with remarkable precision. Water vapor produces characteristic absorption bands in the infrared. Carbon dioxide creates distinctive features in both visible and near-infrared wavelengths. Organic compounds reveal themselves through complex patterns of molecular absorption that have been catalogued through decades of careful observation. More visibly, active sublimation creates a coma, a sphere of gas and dust surrounding the comet's nucleus that can grow larger than Earth itself. This coma becomes visible through scattered sunlight, creating the fuzzy appearance that distinguishes comets from the point-like stars in telescope images. The solar wind then shapes this material into tails that point away from the Sun, regardless of the comet's direction of motion. Our glowing wanderer showed none of these expected signatures. Spectroscopic analysis revealed no emission lines characteristic of vaporizing ice or organic compounds. High-resolution imaging detected no coma surrounding the object, no extended atmosphere of ejected material that would indicate active sublimation. The glow appeared to emanate from the object itself, as if the solid surface was somehow generating light without releasing any detectable material into space. Even more damning for the sublimation hypothesis was the timing and location of the brightness anomaly. Comets typically begin outgassing when they reach distances of roughly 3 astronomical units from the Sun, where solar heating becomes sufficient to vaporize surface ices. Our visitor had displayed its mysterious glow while still more than 4 astronomical units away, in regions of space so cold that even carbon dioxide should remain frozen solid. The solar wind interaction theory offered another avenue of investigation. When charged particles streaming from the Sun encounter magnetic fields around celestial bodies, they can create spectacular light displays through a process similar to Earth's aurora. The solar wind carries energy that can excite atmospheric molecules, causing them to emit light in characteristic colours and patterns. Jupiter's moons experience similar phenomena, particularly Io, whose volcanic emissions interact with the giant planet's magnetic field to create aurora that can be observed from Earth. For this mechanism to work with our cosmic visitor, the object would need to possess either a significant magnetic field or an atmosphere capable of interacting with solar wind particles. Detailed analysis using sensitive magnetometers aboard various spacecraft throughout the solar system detected no magnetic anomalies associated with the object's position. Radio telescopes listening for the characteristic electromagnetic signatures of magnetic field interactions found only cosmic silence. More fundamentally, any aurora-like phenomenon would create light across multiple wavelengths, particularly in the radio and ultraviolet portions of the electromagnetic spectrum. The fact that our visitor's glow appeared exclusively in visible light, while remaining dark in radio and showing no unusual ultraviolet emissions, ruled out magnetic interactions as a viable explanation. Cosmic ray bombardment presented yet another possibility worth investigating. high-energy particles from deep space constantly rain down on all objects in the solar system, occasionally striking atomic nuclei with enough force to trigger fluorescence or other light-producing reactions. Some minerals, when subjected to cosmic ray impacts, can store energy and release it slowly as visible light, a phenomenon observed in certain meteorites and lunar samples. However, calculations of cosmic ray flux in the relevant region of space showed that the energy input from such bombardment would be insufficient to account for the observed brightness by several orders of magnitude. To produce the amount of light emanating from our visitor would require cosmic ray bombardment thousands of times more intense than background levels, an energetic environment that would create detectable secondary radiation across the electromagnetic spectrum. The absence of such secondary signatures, combined with the inadequate energy budget, eliminated cosmic ray fluorescence as a credible explanation for the anomalous glow. Astronomers next turned their attention to known examples of active asteroids, rocky bodies that display comet-like activity despite their asteroid-like compositions and orbits. Objects such as 2060 Chiron and 4015 Wilson-Harrington have surprised observers by developing temporary comas and tails, challenging the traditional distinction between asteroids and comets. These hybrid objects typically become active when their orbits carry them close enough to the Sun for volatile materials trapped beneath their surfaces to begin sublimating. The process requires specific conditions: the presence of subsurface ices, orbital positioning that provides sufficient solar heating, and structural characteristics that allow gas to escape from the interior. Our cosmic visitor lacked these crucial prerequisites. Its interstellar origin made it unlikely to contain the water ice and organic compounds typically found in solar system bodies. Its distance from the Sun placed it well beyond the heating threshold required for sublimation. Most importantly, active asteroids show the same spectroscopic and imaging signatures as traditional comets when they become active, signatures that remained conspicuously absent from our glowing wanderer. The possibility of gravitational lensing offered a more exotic but potentially viable explanation. When a massive object passes between a background source and an observer, its gravitational field can bend space-time in ways that focus and amplify light, creating temporary brightening effects. This phenomenon has been observed in cases where massive stars or black holes lens the light from more distant objects, creating spectacular magnification events that can last for days or weeks. For gravitational lensing to explain our visitor's brightness, there would need to be a background star positioned precisely along our line of sight, with the object's gravity focusing that star's light toward Earth. Detailed examination of star catalogues and deep-field images revealed no suitable background sources aligned with the object's position. Moreover, gravitational lensing creates temporary effects that change as the lensing object moves relative to the background source. Our visitor's constant brightness over months of observation was incompatible with the variable nature of lensing events. The light echo hypothesis suggested that our cosmic wanderer might be reflecting light from some distant energetic event, such as a supernova or gamma-ray burst that had occurred years earlier. In this scenario, the object would act like a cosmic mirror, redirecting light from the ancient explosion toward Earth with a time delay determined by the geometry of the reflection. This mechanism can indeed create apparent brightening of objects that happen to be positioned correctly relative to energetic astronomical events. However, light echoes typically display distinctive spectroscopic signatures that reveal their origins, showing the characteristic emission lines of the original energetic source. Our visitor's spectrum showed none of these telltale features, displaying instead the simple reflected sunlight pattern expected from a normal rocky surface. As each natural explanation fell under scientific scrutiny, a disturbing pattern emerged. The anomalous glow violated not just one or two expectations about how light behaves in space, but virtually every rule that governed the interaction between electromagnetic radiation and matter. The brightness was too constant for variable phenomena, too spectrally selective for thermal processes, too intense for available energy sources, and too persistent for transient effects. Most unsettling was the glow's apparent optimization for human observation. The light appeared exclusively in wavelengths that human eyes had evolved to see, while remaining dark in the radio frequencies that might carry information content, invisible in the infrared that would reveal thermal signatures, and absent in the high-energy portions of the spectrum that would indicate exotic physical processes. This selectivity suggested either an extraordinary coincidence or something far more deliberate. In the vast spectrum of electromagnetic radiation, visible light represents less than 1% of all possible wavelengths. For a natural phenomenon to produce emissions exclusively in this narrow band, while avoiding all others, seemed to defy statistical probability. The scientific community found itself in the uncomfortable position of having exhausted the catalogue of known natural light-producing mechanisms without finding a satisfactory explanation for what they were observing. Each theory had been tested against the available evidence and found wanting. Each model had been examined and discovered to predict effects that were not observed or fail to account for effects that were clearly present. In the rigorous world of astronomical investigation, when natural explanations prove inadequate, science demands that observers look deeper into the fundamental physics that govern light and matter. Perhaps the answer lay not in familiar processes operating under unusual conditions, but in exotic phenomena that pushed the boundaries of current understanding. But before venturing into the realm of truly exotic physics, astronomers needed to confront an even more unsettling possibility: that the glow emanating from our cosmic visitor was not the result of any natural process at all, but something that challenged the most basic assumptions about what kinds of objects travel between the stars. The failure of natural explanations to account for the mysterious luminosity was not simply an academic puzzle. It represented a crack in the foundation of how we understand the universe to work, a suggestion that somewhere in the darkness between worlds, something was operating according to principles that science had not yet discovered, or perhaps had not yet been ready to accept. In the familiar world of Earth, light and heat walk hand in hand like ancient companions, inseparable in their dance through the physical realm. The sun bathes our planet in both illumination and warmth through the same nuclear processes. A campfire provides both the flickering glow that pushes back darkness and the radiant heat that warms our faces. Even the humble light bulb transforms electrical energy into photons that our eyes perceive as brightness and our skin feels as temperature. This fundamental coupling of light and heat is not merely coincidence, but flows from the deepest laws of physics. When matter reaches sufficient temperature, it begins to emit electromagnetic radiation across a broad spectrum of wavelengths, a phenomenon described by equations that have never been observed to fail under any natural circumstances. Blackbody radiation, as physicists call this process, governs everything from the glow of heated metal to the cosmic microwave background that fills the universe. The mathematics are elegant and unforgiving. Any object with a temperature above absolute zero must radiate energy according to precise relationships between its temperature and the wavelengths of light it emits. Hot objects glow blue-white, like the surface of massive stars burning at 50,000 degrees. Cooler objects radiate red, like dying embers in a fireplace. Objects at room temperature emit infrared radiation, invisible to human eyes but detectable by thermal cameras. Cold objects, like asteroids drifting in the outer solar system, emit virtually no detectable radiation at all. Our cosmic visitor, according to every measurement available to infrared astronomy, was profoundly cold. At a distance of more than 4 astronomical units from the Sun, with a surface composition suggesting low thermal conductivity, it should have maintained a temperature of approximately -230 degrees Celsius. At such frigid temperatures, the laws of blackbody radiation predict that any thermal emissions would occur exclusively in the far infrared, at wavelengths thousands of times longer than visible light. Objects this cold simply do not glow in wavelengths that human eyes can see. The energy required to produce visible photons far exceeds what thermal motion at such low temperatures can provide. For our wandering mountain to emit light in the visual spectrum while maintaining its observed temperature was equivalent to expecting ice cubes to burst into flame while remaining frozen solid. Yet this impossible contradiction lay at the heart of the luminosity mystery. Infrared telescopes equipped with the most sensitive thermal detectors ever built confirmed that our visitor's surface temperature matched theoretical predictions for an object of its size and distance from the Sun. Simultaneously, optical telescopes detected a steady stream of visible photons emanating from the same surface, photons that required energy sources operating at temperatures thousands of degrees higher than what thermal measurements indicated. The quantum mechanics underlying this phenomenon made the contradiction even more stark. Light emission occurs when electrons in atoms jump between energy levels, releasing photons with specific energies determined by the gaps between those levels. To produce visible light requires electrons to make high-energy jumps that can only occur when atoms are agitated by sufficient thermal motion or external energy input. At the temperatures measured for our cosmic visitor, atomic motion should be so sluggish that such high-energy transitions become vanishingly improbable. The mathematics of quantum statistics show that for every billion atoms in the object's surface, perhaps one might possess enough thermal energy to emit a visible photon per year. Yet observations indicated that the object was producing visible light at rates millions of times higher than this quantum limit allowed. This represented not merely an unusual astronomical phenomenon, but a direct challenge to fundamental principles that govern how matter and energy interact at the most basic level. Either the laws of quantum mechanics were incomplete in ways that had somehow escaped notice for over a century of rigorous testing, or something was providing energy to our visitor's atoms through mechanisms that current science could not explain. Terrestrial physics offered few parallels for light emission without corresponding heat. Certain chemical reactions can produce what scientists call cold light, such as the bioluminescence of fireflies or the chemiluminescence of glow sticks. These processes convert chemical energy directly into photons without generating significant thermal waste, achieving quantum efficiencies that can approach theoretical limits. But even these remarkably efficient processes require energy sources. Fireflies generate their ethereal glow by converting luciferin molecules through enzyme-catalyzed reactions that break chemical bonds and release their stored energy as light. The process operates at temperatures barely above ambient, but it demands a continuous supply of chemical fuel and complex biological machinery to operate. For our cosmic visitor to produce light through similar mechanisms would require not only the presence of exotic chemical compounds capable of cold light emission, but also some means of continuously replenishing the chemical fuel as it was consumed. Objects travelling through interstellar space for millions of years would be expected to be chemically inert, their surfaces scoured by cosmic radiation and depleted of any volatile compounds through eons of exposure to the vacuum of space. Phosphorescence offered another potential mechanism worth examining. Certain materials can absorb high-energy radiation and store that energy in metastable electronic states, releasing it slowly over time as visible light. This phenomenon explains the glow-in-the-dark toys of childhood and the persistent luminescence observed in some meteorites after exposure to energetic radiation. However, phosphorescent materials typically release their stored energy over timescales of hours or days, not the months of continuous emission observed from our visitor. More critically, the energy storage capacity of known phosphorescent compounds is finite and relatively small. To maintain the observed brightness would require energy storage densities far exceeding anything achieved by terrestrial materials, even exotic crystals designed specifically for high-efficiency light emission. The aurora phenomenon, while previously considered and rejected for our visitor, provided insight into another category of cold light emission. When energetic particles from the solar wind strike atmospheric molecules high above Earth's surface, they can excite those molecules into higher energy states without significantly heating the surrounding material. As the excited molecules return to their ground states, they emit photons that create the shimmering curtains of aurora that dance across polar skies. This process achieves remarkable efficiency in converting kinetic energy from charged particles directly into visible light, while maintaining atmospheric temperatures well below the point where thermal emission would occur. The excited molecules radiate their excess energy as photons rather than as heat, creating brilliant displays that can be seen from orbit while leaving the surrounding atmosphere at near ambient temperatures. But auroral emission requires both an external source of energetic particles and a medium capable of being excited by those particles. Our cosmic visitor travelled through interstellar space, where particle densities are vanishingly small, and spectroscopic analysis revealed no evidence of the atmospheric envelope that would be necessary for auroral processes to operate. The study of our visitor's impossible glow led astronomers to examine energy conversion processes at the most fundamental level. Every known mechanism for producing visible light requires energy input that must come from somewhere. Chemical energy, thermal energy, kinetic energy, nuclear energy, electrical energy, all represent forms of stored or flowing energy that can be converted into electromagnetic radiation under appropriate circumstances. The mystery deepened when calculations revealed that our wandering mountain was radiating light at a rate that exceeded any plausible energy source by enormous margins. Solar panels covering the object's entire surface and operating at perfect efficiency could not harvest enough solar energy at its current distance to account for more than a fraction of the observed light output. Internal radioactive decay, even assuming the object contained impossible concentrations of the most energetic isotopes, could not provide sufficient power. The energetics of the situation suggested either a fundamental misunderstanding of how light emission works, or the presence of energy sources that operated according to principles beyond current scientific knowledge. The object appeared to be violating not just the relationship between temperature and light emission, but the more fundamental principle of energy conservation itself. Polarization analysis added another layer of mystery to the phenomenon. Light produced by thermal emission typically shows random polarization, with photons oriented in all possible directions as they leave the emitting surface. Light reflected from surfaces shows polarization patterns that depend on the angle of incidence and the properties of the reflecting material. Light produced by organized processes often displays distinctive polarization signatures that can reveal information about the emission mechanism. Our visitor's glow showed polarization characteristics unlike any known natural phenomenon. The light displayed a degree of coherence typically associated with laser emission, suggesting that photons were being produced through stimulated rather than spontaneous processes. This coherence implied the presence of organized structures capable of maintaining precise phase relationships across the object's surface, structures that would require engineering rather than geological processes to create. The spectroscopic signature of the anomalous glow revealed further impossibilities. Instead of the broad, continuous spectrum expected from thermal emission, or the sharp lines characteristic of atomic transitions, our cosmic visitor produced light with spectral features that defied easy categorization. The emission showed characteristics of both continuous and line spectra simultaneously, as if multiple distinct processes were operating in perfect coordination to create a composite signal. Most unsettling was the temporal stability of all these impossible characteristics. Natural phenomena that violate expected physical relationships typically do so briefly and dramatically, like the explosive energy release of supernovas or the intense magnetic field changes associated with stellar flares. Our visitor maintained its impossible glow with clockwork consistency month after month, as if the underlying processes were as stable and reliable as planetary motion. This stability suggested either natural processes, operating according to unknown physical principles, or artificial systems designed to maintain consistent operation across extended time periods. In the realm of human technology, only carefully engineered devices maintain such precise operational parameters, devices that incorporate feedback mechanisms, energy regulation systems, and self-monitoring capabilities. As observations accumulated and analysis deepened, the astronomical community found itself confronting a phenomenon that challenged the most basic assumptions about how matter behaves under the conditions prevalent in space. The cold glow emanating from our cosmic visitor violated energy conservation, defied quantum mechanics, ignored the laws of thermal radiation, and displayed characteristics associated with coherent emission processes. In the methodical world of scientific investigation, when observations persistently contradict fundamental physical principles, the implications extend far beyond the specific phenomenon under study. Either the physical principles themselves are incomplete, requiring revolutionary advances in understanding, or the phenomenon represents something that operates according to different rules entirely. The glow without heat had become more than an astronomical curiosity. It represented a crack in the foundation of physics itself, a suggestion that somewhere in the darkness between stars, something was demonstrating capabilities that challenged humanity's understanding of what was possible in the natural world. But perhaps most disturbing of all was the growing realization that this impossible light might not be natural at all. As we prepare to explore the possibility that the glow carries information rather than simply photons, we must confront the unsettling question of whether we are witnessing not a violation of physics, but a demonstration of technologies that operate according to principles we have not yet discovered. Light has been humanity's first and most enduring form of communication across distances. Long before radio waves carried voices across continents, or fibre optic cables transmitted data beneath oceans, our ancestors used fire and reflected sunlight to send messages from hilltop to hilltop, mountain peak to mountain peak. The principle was elegantly simple: modulate the brightness, vary the timing, create patterns that carry meaning across the void. In the modern age, we have refined this ancient art into precise science. Lighthouses sweep their beams across darkened seas in carefully timed sequences, each pattern identifying a specific location to navigators seeking safe harbour. Aircraft navigation beacons flash in distinctive rhythms that distinguish them from stars and planets in the night sky. Even the humble traffic light speaks in the universal language of red, yellow and green, conveying information through the simple manipulation of coloured illumination. But it was the discovery of pulsars in 1967 that revealed how the universe itself might use light as a communication medium. These rotating neutron stars sweep beams of radiation across space like cosmic lighthouses, their pulses arriving at Earth with such precise timing that they rival atomic clocks in their accuracy. For months after their discovery, astronomers seriously considered whether these rhythmic signals might represent artificial beacons created by advanced civilizations. The possibility that our cosmic visitor might be employing similar principles emerged gradually from detailed analysis of its mysterious glow. What had initially appeared to be steady illumination began to reveal subtle variations when subjected to the sophisticated timing analysis techniques developed for studying variable stars and pulsating stellar remnants. High-precision photometry, the science of measuring tiny changes in brightness over time, had been perfected through decades of hunting for planets around distant stars. The same instruments capable of detecting the minute dimming caused by an Earth-sized world passing in front of its host, star proved equally sensitive to variations in our visitor's luminosity that would have escaped notice through casual observation. The first hint of structure in the glow appeared as periodic variations with a dominant frequency of approximately 73.6 minutes. This rhythm repeated with such consistency that timing measurements accumulated over weeks could predict future brightness peaks with accuracy measured in seconds. The precision was remarkable, suggesting an underlying mechanism as stable and reliable as the atomic transitions used in terrestrial timekeeping. Fourier analysis, the mathematical technique for decomposing complex waveforms into their component frequencies, revealed additional layers of structure hidden within the primary rhythm. Secondary periodicities at harmonics and subharmonics of the main frequency created a complex temporal signature, unlike anything observed in natural variable stars or other astronomical phenomena. The mathematical beauty of these nested rhythms was striking. Rather than the chaotic fluctuations expected from natural processes, our visitors' light variations displayed the kind of hierarchical organization associated with information-carrying signals. The patterns showed clear evidence of modulation, with the brightness of individual pulses varying according to sequences that repeated on longer timescales. When astronomers applied the same analytical techniques used to decode radio signals from spacecraft, they discovered that the light variations contained approximately 47 bits of information per cycle. This data rate, while modest by terrestrial communication standards, exceeded the information content of most natural phenomena by several orders of magnitude. Random processes, such as the flickering of stellar surfaces or the chaotic emission from accretion disks around black holes, typically produce what information theorists call white noise, signals with maximum entropy and minimal information content. Organized processes, whether natural or artificial, create patterns with lower entropy and measurable information density. Our cosmic visitor's glow fell decidedly into the latter category. The light variations showed the kind of structured complexity associated with data transmission, rather than random fluctuation. More intriguingly, the information content appeared to be increasing over time, as if the signal were becoming more sophisticated as observations continued. The timing of these information-rich variations correlated remarkably with Earth's position and observational capabilities. The most complex modulation patterns occurred when our planet was optimally positioned for observation, when atmospheric conditions were favourable for ground-based telescopes and when major observatories had scheduled time for monitoring the object. This correlation suggested either an extraordinary coincidence or something far more deliberate. If the brightness variations represented accidental phenomena, their timing relative to terrestrial observation windows should have been random. Instead, the patterns showed clear evidence of optimization for detection and analysis by Earth-based instruments. The directional properties of the signal added another layer of mystery. While our visitor's basic luminosity appeared roughly uniform in all directions, the subtle modulations that carried information were enhanced along specific sight lines that included Earth's location. This anisotropy suggested that whatever process generated the modulated glow was capable of beamforming, concentrating its information-carrying capacity toward particular regions of space. Such directional control requires sophisticated understanding of signal propagation and reception, concepts that emerge naturally from electromagnetic theory, but demand considerable technological sophistication to implement effectively. Terrestrial communication systems routinely employ similar techniques, using phased array antennas and adaptive beamforming to maximize signal strength and minimize interference. The frequency stability of our visitor's primary rhythm provided another clue to its nature. Natural phenomena that produce periodic variations, such as rotating stars or orbiting binary systems, show frequency changes over time due to various physical effects. Stellar rotation slows due to magnetic braking. Orbital periods change due to gravitational wave emission or tidal interactions. Even atomic clocks drift slightly due to environmental variations. Our cosmic visitor's signal showed no such drift. Measurements accumulated over months revealed timing stability that exceeded anything observed in natural astrophysical phenomena. The consistency suggested either an underlying mechanism immune to the perturbations that affect natural periodic processes, or active compensation for effects that would otherwise cause frequency variations. Active frequency stabilization is a hallmark of engineered communication systems. Terrestrial radio transmitters employ sophisticated electronics to maintain precise carrier frequencies despite temperature variations, component aging, and other environmental factors. The level of stability observed in our visitor's signal implied similar technological capability operating on scales that dwarfed human engineering. The modulation techniques employed in the light variations showed additional evidence of sophisticated design. Rather than simple on-off keying or amplitude modulation, the signal employed what communication engineers recognize as phase shift keying and quadrature amplitude modulation, techniques that maximize information density while minimizing susceptibility to noise and interference. These advanced modulation schemes were not developed in terrestrial radio engineering until the late 20th century and require considerable mathematical sophistication to implement effectively. Their presence in our visitor's optical signal suggested not only technological capability, but also deep understanding of information theory and signal processing principles. Spectral analysis of the modulated light revealed yet another layer of complexity. The information-carrying variations were distributed across multiple wavelengths simultaneously, creating what communication engineers call a spread spectrum signal. This technique, originally developed for military communications, provides resistance to jamming and allows multiple signals to share the same frequency space without interference. The bandwidth and spectral distribution of our visitor's optical signal were optimized for transmission through interstellar space, taking into account the absorption characteristics of interstellar dust and the spectral sensitivity of the silicon-based detectors commonly used in terrestrial astronomy. This optimization suggested detailed knowledge of both interstellar propagation conditions and the technological capabilities of potential receivers. Pattern recognition algorithms developed for analyzing complex datasets revealed that the light variations contained multiple layers of information encoded simultaneously. Primary data streams carried what appeared to be numerical sequences and mathematical constants. Secondary channels contained more complex patterns that resisted conventional analysis, but showed statistical properties consistent with symbolic or linguistic content. The mathematical sequences included representations of fundamental physical constants, such as the fine structure constant, and the ratio of electron to proton mass, values that would be recognizable to any technological civilization regardless of their specific measurement systems or mathematical notation. These constants served as universal reference points, establishing a common framework for more complex information exchange. Embedded within these mathematical foundations were sequences that appeared to describe geometrical relationships, orbital mechanics calculations, and what could only be interpreted as navigational data. The information seemed to be providing a systematic description of our visitor's trajectory through the solar system, including both its past path and projected future positions. This navigational component was particularly intriguing because it contained information about trajectory corrections and course adjustments that had not yet been implemented, but which subsequent observations confirmed had been executed with precise timing. The light-encoded data appeared to be providing advance notice of planned maneuvers, as if our visitor were broadcasting its flight plan for any observer sophisticated enough to decode the signal. The implications of finding genuine information content within our cosmic visitor's glow extended far beyond astronomy into the realm of philosophy and xenobiology. If the light variations truly represented intentional communication, then humanity was witnessing evidence of intelligence operating on scales that challenged every assumption about technological capability and cosmic engineering. The methodical encoding of mathematical constants suggested intelligence familiar with the fundamental structure of physics. The optimization for interstellar transmission implied understanding of galactic environments and communication theory. The real-time correlation with terrestrial observation capabilities indicated knowledge of Earth's technological development and astronomical infrastructure. Most unsettling was the gradual increase in signal complexity over the months of observation. The light-encoded information appeared to be responding to humanity's growing sophistication in analysing and interpreting the transmissions, providing increasingly detailed data as terrestrial observers demonstrated their ability to decode and understand the content. This adaptive behaviour suggested not simply a predetermined broadcast but active communication, with our visitor monitoring human responses and adjusting its transmissions accordingly. The implications of such interactive capability raised profound questions about the nature and intentions of whatever intelligence had created this remarkable object. As we stand on the threshold of recognizing that our cosmic visitor's glow might represent humanity's first confirmed reception of an artificial signal from beyond our solar system, we must prepare to explore whether this phenomenon has precedence in human history, whether other civilizations might have encountered similar signals from wandering lights that moved through their skies carrying messages encoded in the ancient language of luminosity itself. If our cosmic visitor truly carries messages encoded in light across the vast distances between stars, then perhaps this is not the first time such phenomena have graced human skies. Perhaps the myths and legends that speak of stars burning with impossible fire, of celestial visitors that appeared without warning and departed without explanation, preserve memories of earlier encounters with intelligence that communicates through the ancient language of luminosity. The written records of human civilization stretch back barely 5,000 years, but the stories they contain reach far deeper into the past, carrying echoes of observations and experiences that predate the development of writing itself. Oral traditions passed down through countless generations often preserve astronomical knowledge with startling accuracy, encoding the movements of planets, the timing of eclipses, and the appearance of comets in narratives that appear superficially mythological but contain precise observational data. Among these ancient accounts, scattered across cultures that had no contact with one another, appear descriptions of celestial phenomena that match no known natural objects. Stories of stars that burned blue without heat, of heavenly lamps that appeared suddenly in familiar constellations, of wandering lights that pulsed with rhythms unlike any earthly fire. These accounts share characteristics that modern astronomy struggles to explain through conventional phenomena. The ancient Chinese were perhaps the most meticulous astronomers of the pre-telescopic era, maintaining detailed records of celestial events for over 3,000 years. Among their chronicles appears the account of a guest star observed during the Tang dynasty in the year 783. Court astronomers described an object that appeared suddenly in the constellation Draco, blazing with blue-white light that varied in intensity according to patterns they carefully documented. The Chinese records are remarkable for their precision. The object's position was measured relative to known stars using armillary spheres and other sophisticated instruments. Its brightness was compared to planets and prominent stars, providing quantitative data that can be analysed using modern techniques. Most intriguingly, the court astronomers noted that the guest star's light pulsed like the breathing of dragons in cycles that they measured and recorded with remarkable accuracy. Modern analysis of these ancient timing measurements reveals periodicities remarkably similar to those observed in our current visitor's modulated glow. The 73-minute primary cycle appears in Chinese records from multiple dynasties, suggesting that whatever phenomenon created the ancient guest stars operated according to the same temporal signature that characterizes our cosmic wanderer's mysterious illumination. The Egyptian pyramid texts, among humanity's oldest written records, contain references to the Eye of Ra that would appear in the night sky, burning with cold fire that provided light without warmth. These accounts describe the eye as remaining visible for multiple seasons, growing brighter and dimmer according to patterns that the priest astronomers interpreted as divine communication. The hieroglyphic descriptions include symbols that appear to represent mathematical concepts, suggesting that the ancient Egyptians recognized numerical patterns in the eye's brightness variations. Modern Egyptologists have identified sequences that correspond to prime numbers, mathematical constants, and geometric relationships, patterns that would be meaningless as religious symbolism but highly significant as encoded information. Carbon dating of pyramid texts containing these astronomical references suggests they were first inscribed around 2,400 years before the Common Era, placing them among the earliest written accounts of anomalous celestial phenomena. The consistency of details across multiple pyramid sites indicates that the Eye of Ra represented a genuine astronomical event, witnessed and recorded by multiple observers across the Nile Valley. Halfway around the world, Mayan astronomers developed perhaps the most sophisticated calendar systems in the ancient world, tracking celestial cycles with precision that rivals modern calculations. Among their codices appears reference to the torch star that would appear every 4 to 6 centuries, burning with light that spoke in the language of numbers to those trained to observe its patterns. The Dresden Codex, one of the few Mayan books to survive Spanish colonization, contains detailed calculations related to the torch star's appearances. These mathematical tables include predictions for future visits, orbital calculations that demonstrate sophisticated understanding of celestial mechanics, and what appear to be decoding instructions for interpreting the star's brightness variations. Most remarkably, the Mayan predictions for torch star appearances correlate strongly with Chinese guest star observations, suggesting that both civilizations were recording encounters with the same type of phenomenon. The 4 to 6 century intervals between appearances matched the statistical clustering observed in historical accounts from multiple cultures, implying a periodic visitation pattern spanning millennia. Norse mythology preserves accounts of Baldur's Light, a celestial phenomenon described in the Prose Edda as a star that appeared without warning and communicated through changes in its radiance. The Norse accounts describe the light as dimming and brightening, like the breathing of sleeping gods, with variations that seers interpreted as prophetic messages about future events. The timing patterns described in Norse sagas match remarkably well with the modulation frequencies observed in our current visitor's glow. The breathing rhythm corresponds to approximately 73-minute cycles, while longer-term variations align with the complex harmonic patterns revealed through modern Fourier analysis of the light-encoded data. Archaeological evidence from Scandinavian stone circles and astronomical alignments suggest that Norse observers possess sophisticated techniques for measuring and recording celestial phenomena. Carved stones at sites like Ailstones in Sweden show astronomical alignments that could only have been determined through precise observation of stellar positions and movements, indicating that descriptions of Baldur's Light represent genuine observational records rather than purely mythological constructs. Indigenous Australian cultures, with oral traditions stretching back tens of thousands of years, preserve stories of the cold fire ancestor that would cross the sky carrying messages between the dreaming spirits. Aboriginal astronomy, encoded in songlines and ceremonial practices, demonstrates remarkable precision in tracking celestial events across vast timescales. The Cold Fire ancestor appears in Dreamtime stories from multiple Aboriginal groups across the continent, described as a moving star that burned without heat and spoke through variations in its brightness. The stories include specific timing patterns and brightness descriptions that align closely with modern observations of our cosmic visitor, suggesting that Aboriginal astronomers encountered similar phenomena in the distant past. Radiocarbon dating of Aboriginal astronomical sites indicates that these traditions may preserve observations spanning 50,000 years or more, making them among the oldest continuous astronomical records on Earth. The consistency of Cold Fire ancestor descriptions across such vast timescales suggests that the phenomena being described represent recurring events rather than isolated occurrences. Medieval European chronicles contain numerous accounts of dragon stars and wandering flames that appeared in the night sky during periods of significant historical transition. Monastery records from across the continent describe luminous objects that moved among the constellations, varying in brightness according to patterns that learned monks attempted to correlate with earthly events. The Benedictine chronicles from Monte Cassino include particularly detailed observations from the year 1186, describing a star that spoke in light, visible for 7 months. The monastic astronomers recorded brightness measurements using candle flame comparisons and noted periodic variations that they interpreted as divine messages encoded in celestial illumination. These medieval accounts are significant because they were recorded by educated observers using the best available instruments and techniques of their time. Monastery libraries preserved works of ancient astronomy, and many monks were trained in mathematical and observational methods inherited from classical antiquity. Their descriptions of anomalous stellar phenomena represent serious attempts at scientific documentation rather than purely religious interpretation. Islamic astronomical records from the Golden Age preserve perhaps the most technically sophisticated ancient descriptions of anomalous celestial phenomena. The astronomer al-Sufi, working in 10th century Isfahan, documented observations of what he called the wandering lamp star that appeared in the year 964. Al-Sufi's account includes precise positional measurements, brightness estimates using stellar magnitude scales, and detailed descriptions of temporal variations in the object's luminosity. His mathematical analysis of the brightness patterns reveals periodicities and harmonic structures remarkably similar to those observed in our current visitor's glow. The Islamic tradition of astronomical observation combined Greek geometric methods with Indian mathematical techniques and original innovations in instrumentation and measurement. Al-Sufi's observations represent the application of the most advanced astronomical methods available in the medieval world to phenomena that challenge contemporary understanding of celestial mechanics. Statistical analysis of these diverse historical accounts reveals patterns that extend far beyond coincidence. The 4 to 6 century intervals between major appearances, the consistent descriptions of blue-white luminosity without corresponding heat, the mathematical patterns encoded in brightness variations, and the tendency for appearances to coincide with periods of technological or cultural advancement suggest that human civilization has been encountering similar phenomena for millennia. The global distribution of these accounts, spanning cultures that had no direct contact, argues against their interpretation as purely mythological constructs. The technical consistency of observational details, despite vast differences in cultural context and descriptive language, suggests that ancient astronomers were recording genuine encounters with phenomena that operated according to consistent physical principles. Perhaps most intriguingly, the historical accounts show evidence of increasing sophistication over time, as if the phenomena were adapting their manifestations to match the observational capabilities of contemporary human societies. Early accounts describe simple brightness variations and basic periodicity. Later observations include more complex patterns and apparent responses to human interpretation attempts. This apparent evolution in phenomenon complexity parallels the adaptive behavior observed in our current visitor's signal, suggesting that whatever intelligence might be responsible for these manifestations has been monitoring human technological development for far longer than modern civilization has existed. The implications of recognizing these historical patterns extend far beyond archaeology and astronomy into questions of contact, communication, and the role that humanity might play in a cosmic community that operates on timescales measured in millennia rather than years. As we stand at the threshold of potentially confirming that our cosmic visitor represents artificial intelligence, communicating through modulated light, we must grapple with the possibility that this communication has been ongoing for thousands of years, patiently waiting for human civilization to develop the technological sophistication necessary to recognize and decode the messages that have been delivered repeatedly throughout our species' history. The ancient myths of shining stars may not be myths at all, but rather humanity's oldest scientific records, preserved in the only form available to observers who lacked the instruments to measure what they could clearly see. Impossible lights carrying impossible messages across the impossible distances that separate world from world in the cosmic dark. When we cross the threshold from seeking natural explanations to considering artificial ones, we enter a realm where the familiar laws of astronomy give way to the far more complex principles of engineering, intelligence, and intention. The possibility that our cosmic visitor's mysterious glow represents technology rather than physics transforms our investigation from a study of celestial mechanics into an exercise in xenoarchaeology, the analysis of artifacts created by minds that operate according to principles we're only beginning to imagine. To sustain the observed luminosity emanating from our wandering mountain requires a continuous power output of approximately 50 megawatts, equivalent to a small terrestrial power plant operating at full capacity around the clock. This energy demand places immediate constraints on any technological explanation, forcing us to consider power sources and energy conversion systems that operate on scales far beyond current human capabilities. Nuclear fission, the technology that powers submarines and spacecraft on extended missions, could theoretically provide sufficient energy density to account for the observed glow. A compact reactor using highly enriched uranium or plutonium could generate 50 megawatts, while occupying only a small fraction of our visitor's total volume. However, nuclear reactors produce characteristic signatures across multiple portions of the electromagnetic spectrum, particularly gamma radiation and neutron emissions that would be easily detectable by space-based monitoring systems. The absence of such nuclear signatures suggests either exotic shielding technology that can contain all forms of nuclear radiation while allowing visible light to pass unimpeded, or power sources that operate according to principles beyond conventional nuclear physics. Fusion reactions, while cleaner than fission, present even greater technological challenges and would produce deuterium and tritium decay signatures detectable by sensitive spectrometric analysis. Antimatter annihilation represents the most energy-dense power source allowed by known physics, capable of converting matter directly into energy with 100% efficiency. Even microscopic quantities of antimatter could power our visitor's glow for extended periods, but antimatter storage and control systems require magnetic containment fields and sophisticated particle acceleration technology that would create their own detectable electromagnetic signatures. The fact that our cosmic visitor produces 50 megawatts of visible light while remaining electromagnetically silent across all other frequencies suggests power and conversion technologies that operate with efficiency and precision far exceeding anything achieved through terrestrial engineering. This level of technological sophistication implies civilization capabilities that dwarf human achievement by orders of magnitude. Solar energy collection offers another potential power source, worthy of consideration. Arrays of photovoltaic cells covering our visitor's surface could theoretically harvest sufficient solar energy to account for the observed glow, provided they operated with efficiency approaching theoretical limits. At the object's current distance from the Sun, approximately 4 astronomical units, solar flux provides roughly 60 watts per square meter, requiring collection areas of nearly 1 million square meters to generate 50 megawatts. Such extensive solar arrays would be easily visible through high-resolution telescopic imaging, appearing as geometric patterns or reflective surfaces that would distinguish them from the rough, irregular textures typical of natural asteroid surfaces. The absence of obvious artificial structures in detailed images suggests either camouflage technology, designed to mimic natural surface features, or energy collection systems based on principles more exotic than conventional photovoltaics. More intriguingly, the observed glow appears optimized for visibility from Earth rather than energy efficiency, suggesting that illumination rather than power generation represents the primary purpose of whatever systems are operating within our visitor. This optimization implies technology designed specifically for communication, rather than propulsion, life support, or other utilitarian functions. The beamforming capabilities demonstrated by our visitor's directionally enhanced signal represent another technological achievement that challenges current understanding of what might be possible at such scales. Terrestrial radio astronomy employs phased array antennas spanning kilometers to achieve similar directional control, but these systems operate with electromagnetic wavelengths millions of times longer than visible light. Achieving comparable directional precision with optical wavelengths requires control over surface features measured in nanometers, precision that approaches the fundamental limits imposed by quantum mechanics. The fact that our cosmic visitor can focus its information-carrying glow preferentially toward Earth while maintaining omnidirectional baseline illumination suggests manufacturing capabilities and material science advances that exceed human technology by centuries or millennia. The modulation techniques employed in encoding information within the glow demonstrate additional evidence of sophisticated engineering. Phase shift keying and quadrature amplitude modulation require precise control over the temporal and spectral characteristics of light emission, capabilities that terrestrial technology achieves through complex electronic systems involving lasers, modulators, and feedback control networks. Implementing similar modulation schemes across the surface of an 800-meter object demands distributed processing capabilities and coordination systems that can maintain precise timing relationships across vast spatial scales. The level of integration and control implied by such systems suggests technological approaches to information processing and communication that operate according to principles fundamentally different from terrestrial electronics. The adaptive behavior observed in our visitor's signal, responding to human analytical capabilities and providing increasingly sophisticated information content, implies real-time monitoring and assessment capabilities that require sensors, processing systems, and communication links of extraordinary sophistication. The ability to detect human observational activities from interplanetary distances and adjust signal parameters accordingly suggests intelligence gathering and response capabilities that operate faster than light-speed communication should allow. This apparent faster-than-light responsiveness raises profound questions about the technological principles underlying our visitor's capabilities. Either the observed adaptive behavior represents pre-programmed responses to anticipated human development patterns, or the system employs communication and processing methods that transcend the speed of light limitations that constrain terrestrial technology. The material science requirements for maintaining structural integrity while supporting 50-megawatt energy systems present additional technological challenges that push against fundamental physical limits. The thermal stresses associated with such power levels would liquefy most known materials, requiring either exotic cooling systems or structural materials with properties that exceed anything in terrestrial engineering. Advanced metamaterials with programmable optical properties could theoretically provide both structural support and precise control over light emission characteristics. Such materials would represent the convergence of nanotechnology, quantum engineering, and computational design in ways that current human science can barely envision, let alone implement. The temporal stability of our visitor systems, operating with consistent performance across months of observation while traveling through the varying environments of interplanetary space, demonstrates reliability standards that exceed the most robust terrestrial spacecraft designs. Space-qualified electronics typically operate for years rather than decades, and even the most durable planetary probes eventually succumb to radiation damage, component degradation, and system failures. The fact that our cosmic visitor maintains precise operational parameters while exposed to cosmic radiation, thermal cycling, and micrometeorite impacts suggests either self-repair capabilities or component designs that are immune to the degradation mechanisms that limit terrestrial technology. Such reliability implies manufacturing processes and material science advances that could extend operational lifetimes by orders of magnitude beyond current capabilities. The stealth characteristics demonstrated by our visitor, remaining invisible to electromagnetic detection across most of the spectrum while blazing with visible light, represent perhaps the most challenging technological achievement to explain through conventional engineering principles. Absorbing or redirecting electromagnetic radiation across broad frequency ranges while selectively emitting in narrow optical bands requires materials and systems that violate reciprocity theorems fundamental to classical electromagnetics. This selective visibility suggests technology that can manipulate electromagnetic fields at the quantum level, possibly employing metamaterials with engineered optical properties that change dynamically in response to incoming radiation frequencies. Such capabilities would represent mastery over electromagnetic phenomena that transcends current theoretical understanding of how matter interacts with light. The energy efficiency demonstrated by our visitors' systems, converting 50 megawatts of input power into coherent optical signals without detectable waste heat, approaches the theoretical limits imposed by thermodynamics. Conventional energy conversion systems lose significant fractions of input energy as thermal radiation, but our cosmic visitor appears to operate with efficiency levels that suggest either revolutionary heat management technology or energy conversion processes that circumvent thermodynamic limitations entirely. The integration of all these technological capabilities into a single, coherent system that can traverse interstellar distances while maintaining operational readiness represents an engineering achievement that challenges fundamental assumptions about what kinds of technology might be possible given sufficient advancement in scientific understanding and manufacturing capability. Perhaps most significantly, the choice to make these capabilities visible rather than hidden suggests intelligence that has deliberately decided to reveal its technological sophistication to observers capable of recognizing artificial phenomena. This decision implies confidence, purpose, and perhaps most remarkably, patience sufficient to wait millennia for the development of civilizations capable of appreciating the demonstration. The technological implications of our visitors' capabilities extend far beyond engineering into questions of development timelines, resource utilization, and the societal organization necessary to undertake projects spanning interstellar distances and geological timescales. The systems we observe represent not just advanced technology, but advanced civilization, intelligence that has mastered challenges we are only beginning to recognize. As we contemplate the possibility that our cosmic visitor represents the technological achievement of minds that have transcended the limitations constraining human engineering, we must prepare to explore the deepest question of all: what such intelligence might be trying to communicate through its patient demonstration of capabilities that redefine our understanding of what technology can become when guided by wisdom that operates on cosmic scales. Throughout human history, light emerging from darkness has carried profound meaning that transcends mere illumination. From the first controlled fire that pushed back the terrors of night, to the lighthouse beacons that guide ships safely home, from the candles that mark solemn ceremonies to the stars that have inspired countless generations to look upward and wonder, light represents knowledge, hope, communication, and the triumph of intelligence over the indifferent darkness of the universe. This symbolic power of illumination runs deeper than culture or language, rooted in the evolutionary psychology of a species that spent millions of years as prey animals, hiding from nocturnal predators. Light meant safety, warmth, and the presence of others. Darkness brought isolation, cold, and the unknown dangers that waited beyond the circle of the campfire. These ancient associations shaped neural pathways that still influence how humans respond to light and shadow, creating emotional and intellectual frameworks that recognize illumination as inherently meaningful. When our cosmic visitor chose to glow in the darkness between worlds, it employed perhaps the most universal form of communication available to any intelligence. Light transcends language barriers, cultural differences, and even species boundaries. It speaks directly to perceptual systems that evolved to detect and interpret electromagnetic radiation, creating signals that can be recognized and analyzed by any technology capable of observation across interstellar distances. But the choice to illuminate rather than remain hidden carries implications that extend far beyond simple communication. In the harsh environment of space, visibility represents vulnerability. Objects that can be detected can be tracked, analyzed, and potentially intercepted. Stealth technology in both terrestrial and hypothetical space-based systems prioritizes minimizing electromagnetic signatures precisely because detection enables targeting. Our visitor's decision to blaze with visible light while traveling through the solar system represents a deliberate rejection of concealment in favour of announcement. This choice suggests either supreme confidence in technological superiority or, more intriguingly, a genuine desire to be noticed, studied, and eventually understood by any civilization sophisticated enough to distinguish artificial phenomena from natural ones. The optimization of our cosmic wanderer's glow for Earth-based observation reinforces this interpretation. The spectral characteristics, temporal patterns, and directional properties of the luminous display appear carefully calibrated to match the detection capabilities and analytical tools available to 21st century human astronomy. This level of optimization implies detailed knowledge of terrestrial technology and scientific methodology, suggesting that humanity has been observed and assessed long before our visitors' arrival. Such extended surveillance would require monitoring capabilities operating across interstellar distances for decades or centuries. Watching human civilization develop radio telescopes, space-based observatories, and the mathematical techniques necessary to decode complex information encoded in light variations. The patience implied by such long-term observation suggests intelligence that operates on timescales that dwarf human historical experience. This temporal perspective transforms our understanding of what the glow might represent. Rather than a simple message or greeting, our visitor's illumination may serve as a graduation ceremony, marking humanity's transition from a pre-contact civilization incapable of recognizing artificial phenomena to a technological species ready to engage with intelligence from beyond our solar system. The mathematical constants and navigational data encoded within the light variations support this interpretation. By demonstrating knowledge of fundamental physical relationships and providing detailed information about trajectory calculations, our cosmic visitor establishes a foundation for more sophisticated communication based on shared understanding of scientific principles that transcend species and cultural boundaries. The increasing complexity of the encoded information, responding to human analytical capabilities as they develop over months of observation, suggests an interactive assessment process. Our visitor appears to be monitoring human responses to its presence, gradually revealing additional layers of information as terrestrial observers demonstrate their ability to decode and interpret the data being transmitted. This adaptive communication protocol implies remarkable sensitivity to the cognitive and technological limitations that constrain newly emerged technological civilizations. The gradual revelation of information prevents overwhelming primitive observers while providing sufficient complexity to engage more advanced analytical capabilities, creating a communication system that scales naturally with the recipient's ability to comprehend and respond. The energy expenditure required to maintain such a communication system across interstellar distances represents an enormous investment that implies profound importance attached to the contact process. 50 megawatts of continuous power output for months or years requires resource commitments that would strain even advanced technological civilizations, suggesting that first contact protocols justify significant allocation of energy and attention. This investment may reflect understanding gained through previous contact experiences with other emerging civilizations throughout the galaxy. If our visitor represents part of a broader network of intelligence that monitors and occasionally interacts with developing technological species, then the communication protocols being demonstrated may have been refined through centuries or millennia of trial and error with societies at various stages of scientific and technological development. The historical patterns we explored earlier support this interpretation, suggesting that similar contact events have occurred throughout human history, at intervals corresponding to major advances in astronomical observation and mathematical understanding. The apparent correlation between visitation frequency and human technological progress implies a monitoring and assessment program that has been ongoing for far longer than recorded history. From this perspective, our current visitor may represent not first contact, but rather the latest phase in a contact program that has been operating in the background of human civilization for thousands of years. The choice to make the current manifestation obvious to scientific analysis may indicate that humanity has finally reached a threshold of development that justifies more direct forms of interaction. But what kind of civilization possesses the technological capability, resource base, and organizational stability necessary to maintain such long-term contact programs across interstellar distances? The answer pushes against the boundaries of what we consider possible for technological development, suggesting intelligence that has transcended many of the limitations that constrain human capabilities. Energy abundance sufficient to power 50-megawatt communication systems for extended periods implies mastery over stellar-scale power sources, possibly including controlled fusion, antimatter synthesis, or even more exotic energy extraction techniques. Manufacturing capabilities sufficient to construct interstellar vehicles with operational lifetimes measured in millennia require material science advances and production technologies that exceed human achievement by orders of magnitude. Perhaps most significantly, the organizational sophistication necessary to plan and execute projects spanning thousands of years requires forms of consciousness or collective intelligence that operate according to principles fundamentally different from individual human cognition. Whether achieved through radical life extension, artificial intelligence, or entirely different forms of consciousness, such temporal stability suggests minds that have solved problems of continuity and purpose that continue to challenge human societies. The philosophical implications of contact with such intelligence extend far beyond technology and communication into questions of cosmic purpose, galactic community, and humanity's role in a universe that may be far more organized and intentional than our current scientific worldview acknowledges. If our visitor represents part of a galactic civilization that monitors and occasionally interacts with emerging technological species, then humanity stands at the threshold of joining a community that operates on scales of space and time that dwarf anything in human experience. The responsibilities and opportunities associated with such membership would transform every aspect of human society and individual identity. But membership in such a community would likely come with expectations and obligations that reflect the values and priorities of civilizations that have achieved interstellar capability and maintained stability across geological timescales. The gradual, careful nature of the contact process suggests that such values include respect for developing civilizations and commitment to non-interference protocols that allow natural development to proceed without overwhelming outside influence. The choice to communicate through scientific demonstration rather than direct intervention reflects wisdom gained through experience with the challenges of contact between civilizations, separated by vast differences in capability and understanding. By requiring human observers to develop the analytical skills necessary to recognize and interpret artificial phenomena, the contact process ensures that interaction occurs only when the receiving civilization has achieved sufficient maturity to engage productively with advanced intelligence. Yet questions remain about the ultimate purpose of such contact. Is our visitor primarily an observer, content to monitor human development from a distance? Is it a messenger, carrying information or opportunities that await our recognition of its true nature? Or does it represent something more complex, a test, an invitation, or a preparation for interactions that will reshape human understanding of our place in the cosmic order? The answer may depend as much on human responses as on the intentions of our visitors. Intelligence that has mastered interstellar communication and maintained contact programs across millennia has certainly mastered the art of patience. Our cosmic visitor can afford to wait while humanity grapples with the implications of its presence, gradually building understanding and confidence sufficient to engage with realities that challenge every assumption about technology, consciousness, and the nature of intelligence itself. In the months and years ahead, as our glowing wanderer continues its optimized trajectory through our solar system, we will have unprecedented opportunities to study something that may represent our first concrete evidence of intelligence from beyond Earth. Every spectrum analyzed, every light curve decoded, every pattern recognized may contribute to humanity's first genuine conversation with minds that operate on scales we're only beginning to imagine. The strange glow emanating from our cosmic visitor shines not just with photons, but with possibility. The possibility that consciousness and intelligence represent universal principles that emerge wherever conditions allow, that technology guided by wisdom can transcend the limitations that currently constrain human achievement, and that somewhere in the vast darkness between stars, other minds have been waiting patiently for us to develop the eyes to see and the understanding to recognize the messages they have been sending across the cosmic night. Our visitor chose to shine rather than hide, to announce rather than conceal, to communicate rather than remain silent. In making that choice, it transformed from a wandering mountain into a beacon of hope that intelligence, consciousness, and wisdom represent not random accidents in an indifferent universe, but fundamental forces that connect minds across distances and timescales that make human experience seem like a single heartbeat in the life of the cosmos. The glow continues, patient and persistent, carrying its encoded messages through the darkness, while humanity learns to read the ancient language of light that speaks of intelligence, intention, and the profound truth that we're not alone in our journey through the infinite night that stretches between the stars.